Thank you very much, Professor Smaluch. It's a great pleasure to be here. And from the conversations that we have this afternoon and the day before, I find myself fortunate to be invited by the center, by the WPI, and fortunate to have these conversations, because as you can see, many of the issues that this community of scientists which are interested in chirality and knots, and you will see in complexity of matter, and unifying rules of topology are also the questions that I'm interested in. And you will see them gradually. I would like to talk to you today about complexity. The enumeration of complexity includes some new math. And in this case, this is the graph theory. I will also show you that unlike the very common understanding of chirality among the scientists, especially in chemistry, chirality is a continuum, and we have a number of examples of that. And finally, I would like to extend it even beyond the chiral structures and show some early results, how topological or topometric relationships can be found in other structures, for instance, in composites. Chiral nanostructures is expanding very rapidly. This is a field where most of the people are very much interested in hyperoptical activity, because the nanostructures, being metals or semiconductors, have a giant polarization rotation. They're also inherently biomimetic. Chirality is a unifying factor for biology, for proteins, and nanoparticles in the same time. Also, the chirality in both worlds, as we will see, are multi-scale. And this leads me to the topic, which is the complexity. And the motivation for this topic comes also from the biomimetic and bio-inspired structures that are also quite useful. And one example of those are these tissues, enamel, bone, and cartilage. And you can see some of the very unifying patterns in the organization of these tissues. They're all self-assembled. They're made from nanoscale systems, nanoscale pieces, and they're all chiral. Another piece is maybe less obvious, but it's very essential for both how they are made and what they're serving for. So in all of these cases, they have non-crystalline order. And this combination of order and disorder and non-crystallinity, yet non-randomness, is why cartilage can serve us for 50 years, for some at least, and not fail. And we abuse it extensively. And despite that, this kind of nanofibrous architectures can realign themselves and adapt to the load. Another example of complex particles in this case can be seen by looking at viruses or algae or pollen. And we can again see that they are made from chiral, self-assembled nanoscale pieces. They also have non-crystalline order. And in addition to that, there is a certain topological pattern which is unifying them across the scale. These are basically spiky balls. And you will see that these spiky balls are actually essential for their functions, and their structure can be uniformly described in this manner. So now we see that there is a structural similarity between all of them. There is obvious usefulness of all of them, and we now need to understand how to engineer them. Well, the first entrance in this area was done actually quite some time ago by Ray Gilman. Some of you know that he was the inventor, if you want, the theory of quarks. And later in his career, he started interested in the idea of complexity. And he introduced the concept that the complexity as applied to biological structures is actually a combination of order and disorder. And it maximizes when there is a mixture of these two. So you can envision it in this way, that if you have a crystal or you have a gas, the way to describe the structures is quite easy. It has a certain distance between the rows of atoms, or just completely random. In both cases, the pattern is actually quite easy. The problem here that it is a notional concept, that there are no numbers here, he just drew it. And as a kind of a coffee topic, that's perfectly nice. As a tool to engineer the nanoscale materials, it is not. And that's what I would like to change. For example, you can have all these wonderful materials and you have no idea if they are more complex or less complex than each other, or if you can tune them a little bit, you can make even better structures. Nanoparticles represent a very good example of the system that can be used to test and quantify the complexity as well as the degree of order and disorder. They can be chiral, they self-assemble, they're also quite functional. There are lots of materials that we're using now from them, and they can be very easily imaged in electron microscopy with high contrast, unlike, for instance, the proteins or the collagen fibers. There are a couple of problems there, though. First problem, that nanoparticles, unlike, for instance, amino acids or peptides or proteins, they are actually not identical to each other. They have always some dispersity. And it could be the number of atoms, could be a number of ligands, could be sizes. But anyway, it is unclear if we are on the other side of the curve and can be completely random. The other part is maybe less appreciated, is the fact that complex structures inevitably are thermodynamically less favorable. And if we look at the system, how particles or other nanoscale structures self-assembled, they all want to be in actually high mass states, which maximize the van der Waals attraction, and therefore not complex. These states are always higher in energy. So we need to have some kind of internal barrier in that system that prevents the particles in getting into this area. What it can be, it's actually not very easy to do, but the previous experiences that I had since postdoc showed me that we actually have electrostatic barrier in self-assembled systems, and it's very effective. For example, the layers or bilayers of clay or graphene oxide or other nanosheets assemble only one layer on the surfaces. The next layer of nanosheets is repulsed and prevented from adhesion by electrostatic repulsion. And in this example, you can also see that there is element of symmetry as well, because these are platelets, and they always absorb in a particular orientation to the substrate. And this is important because it's an additional restriction that plays a role. So it's one electrostatic, one symmetric. And one good example of that and how useful it is, these are nacre-like structures of graphene oxide or clay or other systems which are very common. So it can also occur not only on the surfaces, but in liquids. For example, we can see the formation of supraparticles. Here, we also have the same electrostatic repulsive barrier. When the supraparticle reaches certain size, about 100 nanometers or 200, 300 particles, this electrostatic barrier says no more, and all the new particles repulsed. So beyond this size, the system cannot go. But now the question is how symmetry restrictions or chirality can change and make it or not more complex. And we decided to test this hypothesis by using the nanosheets. These are a gold sulfide two-dimensional material. On top and the bottom of this nanosheets, we have chiral ligands, L-cysteine or D-cysteine. And of course, having the chirality at molecular level, these nanosheets will be slightly twisted. It's not visible on electron microscopy, but it's very visible in self-organization. And the dispersity of the nanosheets that we have here is very wide. If they form something interesting, this will also be indicative of the fact that even such huge dispersity is not a problem for making complex structures. Here it is. So we saw the formation of the hedgehog particles. They are also quite uniform in size. When ligands are L-cysteine, when they are racemic, they've also formed quite interesting particles that have a repeating pattern of shapes. For instance, they are asymmetric, there is a stacking of sheets, and they look like the crosses. If we change the chirality of the ligand to D-cysteine, we also have the hedgehog particles. But the difference comes very vividly when we look at the geometry of the spikes. Depending whether your ligand is L-cysteine or D-cysteine, the ribbons which form the spikes, they twisted left or right, respectively, and they also fan left or counterclockwise or clockwise. And so this results in particles which have the similarities, but also quite distinctly different in hierarchical organization. If we look at the role of not only chiral restrictions or hydrogen bond restrictions, which are responsible for this packing, we can notice that the electrostatic restrictions are also very strong. And these are the uniform particles which are made in buckets. And this is the reason why they can be very useful. And maybe this is the reason why say, liposomes or some exosomes, they have a particular size because of this electrostatic restriction. And these particles just indicate that we can harness this restriction for something else. Let's change the chirality of the system by tuning the enantiomeric excess of L and D cysteine. On top, it's our L, on bottom, it's all D. And if you look at the geometry of the particles, you notice now that they are very different and maybe variable in complexity. For instance, these supraparticles from nanosheets may be not so complex, but here we have this twisted bundles which becoming visually more complex, or the stars, or the supraparticles of supraparticles. The hedgehogs are here and in the other corner. So now the question emerges, how do we decide objectively what is the complexity measure of these particles? And we also want this to be applicable not only to a particular shape or a particular type of building blocks, but to all of the nanoparticle assemblies, to chains, to the nacre-like structures, to supraparticle superlattices, and other systems. The approach that we took is based on the graph theory. And maybe you know it, but just in case, graph theory is nothing but a segment of discrete mathematics which deals with the sets of nodes and edges. Edges are connecting the nodes, and it can have different compositions. They could be bipartite or monopartite, have some segments which are more connected, less connected. There are the whole set of multiple books which describe the different graphs and networks. The reason why graph theory is particularly good to answer the previous question is because complexity has a number of measures there. And we can choose what we like and how it would be the best to address that question about effective complexity. We can use the multifractality, or how different patterns are changed with the scale of the graph, or connectivity index, so how many neighbors locally or on average nodes have, or complexity index, which had been originally worked out for organic molecules by Randich and Plage. So what I did during the pandemic time is developing the graph theory for the nanoscale structures. And for that, we needed to expand the measures of complexity to infinite number of particles, and to the particles which do not have a specific size as atoms, for instance, in organic chemistry, as Randich and Plage were using. It turns out not too difficult, but requires a little bit of attention to dispersity as the particles are. So one simple first step, that a particle can be described as a node or a K1 full graph. Importantly, that here we treat the particle not as an ideal spherical object, but it can have very non-spherical object as long as there is no pattern in that shape. So it can vary, bumpiness in, or maybe even elongated or not, but as long as there is no a specific repeatability in, for instance, aspect ratio or pattern of the bump, it has to be described as K1. If the particles are connected, normally it's through the organic layer, it will be described as an edge. That is it. That is very simple. More everything else is about how to describe properly the difference between particles and atoms. So if the particle has a preferential rod-like shape, and it doesn't need to be any perfect, so it has certain variability there. It is a K2 graph. If it is a platelet, it is a K3 graph. And this is already becoming very intuitive. So the plate or a rod is described by these points always. If the particle is chiral, it has to be described by a K5 graph, which is the first three-dimensional graph in the simplest form. And the idea here is not only that we describe particles in some way, but we minimize their complexity in their description. So minimization is critical because you can always increase the complexity to the infinity. If you minimize it, it becomes absolute. It's like the absolute temperature. So now we can also apply the same methodology. If they are connected, there are edges. This also leads us to something interesting, that we can look at edges and assign certain values to them as well. So this might be weights. It's something that we have been working on now. Not all edges can be identical to each other. So the formula to calculate the complexity index is actually easy. So it depends on the pattern, how they're organized, and the number of neighbors. So you basically add in the diminishing contribution, the number of neighbors, next neighbors, next neighbors, etc., etc. And let's see if that complexity index matches our maybe maybe naive or expectation what complexity is. It actually does. Single particles, complexity 1. Pair of particles, 1.5. It's bigger, it's slightly larger, so it's maybe slightly more useful as well. Chirality immediately increases the complexity to 12. You remember that crystallinity actually not necessarily the highest degree of complexity, right? So it should be fairly low. And we calculated the complexity of these chains, which are one-dimensional crystals, and their complexity is 6. So indeed, it's higher than, say, 1 particle or 2 particles, but not as high as a chiral particle. And this is the representation of the fact that the rule here is identical. So you can make a number of the repeat units, but the repeat units are still identical. So what about these structures? More complex. One of them is supraparticle, which is described by this loop, made from nanosheets. And the other case is a nacre-like assembly, so the stack of the sheets, and the organization here is very much descriptive how the connections between the nanosheets are made here. These are random, but here they are organized. And these are the organic layers in between the sheets. The complexity index here is 6, which makes sense. And here it's even more sense, it's equal to 24. One point of that image and that calculation of complexity index is that nacre is a very useful material. So when you add nacre-like structures, they're used in laminates, they're used in computers. If you had today some kind of packaged food, the laminates on packaged food are nacre-like structures, so to prevent the transport of gas. So this is very common and very useful. So if you have a complexity index of 24, it basically indicates already this structure should be good for a lot of things. What about this? The kayak particles, the ones that are racemic, complexity index 40, and these are 87. So the chirality really boosts the complexity of the structure. And I took a liberty and compared the prototype of the chiral hedgehogs with themselves, and we found that the complexity of algae particles or coccolith is actually smaller than the complexity of the lead-made particles. It's certainly not an obvious thing, because we expect that biological entities will be more complex. They are from living things. This is not living thing. But as we go very stringently through the steps of identification of building blocks, they're chiral, yes, they're chiral. How they're organized in spikes or the ribbons. They're organized around the empty core. So if we go through the electron microscopy data on their geometry and patterns of organization, we inevitably come to the lower number than this. I don't want to take too much kind of excitement, or there shouldn't be too much excitement about it, because we can make complex structures in the lab. We can make the more complex structures than the living systems. It's just a matter whether the living system, like algae, actually needs that complexity. It does not need too high complexity. And that's one of the lessons of engineering of biomimetic systems. You don't want to have the complexity just for fun. You want the complexity at the minimal level, and you need to have a measure to evaluate it ahead of time. You don't want to make the chiral hedgehogs unless you need a specific functionality for them, for instance, the catalytic activity or optical activity. This approach applicable to other particles. They are very in complexity, and we can measure it. Importantly, this gives us not only a comparison, but also a method to write the formula of the particles, which is quite novel and hadn't been attempted before. So now you have an analog of atomistic models or atomistic formulae that we all used, for instance, for methane or benzene or amino acid. And this is an important step in utilization of, say, machine learning for the design of complex particles, because unless you have a method to quantify, describe in the terms which computer understands much better than images, the structure of the particles, you have more difficult time to engineer and to machine learn it. So back to this phase diagram, and we now have tools to ask and answer this question about which of them more complex. This is the map of complexity index, and here are some of the expected things and some unexpected. One part which is expected is that the chiral hedgehogs correspond to the highest complexity and to the highest chirality. So for chiral hedgehogs, it is like the perfect expectations, high chirality, high complexity, but unless we map it, unless we actually calculate it for everything else, we may expect that in order to get complex, good particles, you just need to increase the chirality. This is not the case. And for example, these particles are very chiral systems, but their complexity is small. These particles, these are kayak particles that you saw before, they are racemic, or their chirality is small, but their complexity is actually decent. And as we increase the chirality, we may increase the complexity, but that can also drop later on. So this similar experiment, but maybe in one-dimensional form, can be done by replacing L-cysteine with a chiral ligand, which also form these nanosheets. This is thioglycolic acid. Adding a little bit to chiral hedgehogs, complexity drops immediately to this random agglomerates that we didn't want the system to acquire. These are messy structures that are also ugly. But if we increase the concentration of thioglycolic acid a little more, that becomes a little better. These dumbbells are actually not too bad. Their complexity is higher. Then it drops again, then it increases back. So this is maybe some of the points which can summarize the entire study in a very simple way. The chirality is important for complexity. It is a factor why you and I emerged eventually, because we are fairly complex systems. But the mechanism of increase of complexity, mechanism how the sophistication of organization of these patterns from random to non-random actually emerges is not because our molecules are monochiral, but because the monochirality induces the competition of restrictions. So electrostatic restriction is always there. Chiral restrictions involve many of them. Hydrogen bonding, they involve the mechanics, they involve packing. And if these restrictions compete with each other, if they contradict other restrictions, then the system becomes more complex. And this is critical because it's actually a very simple way how to make the systems of increasing hierarchical complexity, and I will show you it in the next slide. But it also gives idea why chirality is significant, because if you look at chirality, it retains the chiral or mirror symmetry from scale to scale to scale, not just from molecule, but also at nanoparticle, at microparticles, at millimeter scale. So as we increase in scale, the chirality persists. And therefore, the different restrictions can come in at different levels, and that's how we evolve. There is interesting contradictions there, and I wonder if anyone would notice it. It's related to left and right hands, but we can chat about it later. So. How do we use that knowledge? Well, let's try to engineer more particles, and some of them are bow ties. So these are stack of twisted ribbons. They're somewhat similar to these bundles that you saw before. In this case, they're made from cadmium cystainate, and cysteine is a dipeptide of cysteine. Their complexity index is fairly high, nice and well. The electrostatic restrictions are still at play. You can see it by the uniformity of dimensions and shapes, and it can be seen from these electron microscopies, even at the increased scales. The difference with chiral hedgehogs is that we change the composition and we can change the chirality, but the shape of the particles does not change. Or if you want, the topological description of the particle does not change. So in the chiral hedgehogs, if you change the concentration of L-cysteine and D-cysteine, it changes dramatically from hedgehogs to more smooth particles. Here, it's always this twisted bow-type shapes. They can be smaller, they can be thicker, they can be more twisted, less twisted, but they always retain that geometry. And this is very good because we can trace a number of optical and other effects, and also we can state that they retain the same hierarchical organization regardless of the conditions, and they combine the molecular level, the level of this individual twisted nanoribbons, which are stacked in the fanning bundles, which eventually stacked and combined in the bow ties. In conjunction with these different scales, we see matching data in spectroscopy. For example, the molecular scale chirality corresponds to, say, angstrom distances, and we can see it in VCD. These are vibrations. The nanoscale chirality can be seen in the vibrations that extend over the entire nanosheet, over the entire length. So these are chiral phonons that are launched over the entire nanoribbon, and they're quite strong here. The entire particle results in electron circular dichroism or standard circular dichroism in visible and near infrared range. You change the size of the particle and you change the position of the peaks very strongly. In fact, the regularity of that shift is quite attractive for a number of engineering applications, and that's the reason why the control of complexity is so attractive, because you can now tune particles for specific, for instance, resonance state. We understand the origin of these peaks, and they are combined from two scattering and one absorptive peak. One is dipolar scattering, the other one is quadrupolar. And by and large, these peaks and this regression is very much similar to the quantum dots effect or in semiconductor particles or gold, the plasmonic effects. You change the size, you change the resonator, and that's the only thing that matters there. So here the resonator is entire particle, and it's a dielectric resonator, not metallic like in gold, or not semiconductor or excitonic as in the semiconductor. One quite interesting outcome here is that once you vary the geometry, once you vary the pitch, you quickly see that now you have a quite different animal than any other chiral chemical structure. It's not L or G amino acids, for instance, not peptides of no helicines, which have very fixed binary chirality, which basically blocks thinking about the chirality as a physical entity and how to connect chemical chirality to mathematical chirality. Here we have the continuum of chiral state, and we can gradually change pitch to the smallest degree just by changing the concentrations. And this gives us an opportunity to address some of the old problems. If you attended the conference on circular dichroism, which is happening now in the downtown, Bart Carr gave exceptionally good talk about the chirality measures. It turns out that chirality measures, or measures of geometrical chirality, which are applicable to any scale, turns out to be quite useless in applications. They're not used in drug design, although you think they would be. They're not used in predicting the optical activity, and Bart had demonstrated it very nicely. There is also a problem of so-called chiral zeros, which is associated with the Osipov pickup the Hamburg chirality index. It has positive and negative sides. It seems to be quite convenient, just like positive circular dichroism peak and negative circular dichroism peak. But there is a statement, or there are a number of studies from very intelligent and deep thinking scientists like Kurt Mislow or Tom Lubensky and Randy Kamian, who state, well, if you have a chirality measure with this parameters, it should be positive and negative and zero and achiral, it makes no sense because there always be chiral structures that will give you a chiral zero which will be false. And they determine it mathematically. And I thought, why nobody try to look at it experimentally? And I did. And the bow ties showed very convenient case, and I plotted OPD, or Osipov pickup the Hamburg chirality index, versus, for instance, their lambda, the position of the spectrum, and you see nearly perfect sequence and mapping between OPD and the optical properties. And of course, I was very excited. I didn't know what is going on, why smart people say that it cannot be. And it turns out that the explanation is actually quite easy. The reason is that Mislow and Randy Cambion and Tom Lubensky, they say, well, we will take some pathway of reconfiguration that system of 4 points in some way. If there is no restriction on the pathway, it can go through chiral states, which give you 0 in the measure. But for the bow ties, this is not true. You actually fixed their configuration. It's just a twisting, gradual twisting of the structure. It's not like we're stretching or doing some other crazy things or making some kind of peninsula. The pathway goes very definitively through a chiral state. Under the circumstances, the system becomes very well behaving, and the chiral 0 problem disappears. The reason why we actually have such a good dependence with optics is because we actually have multiple chirality measures. We can have the chirality measures for this, or for that, or for that, but we took for the entire particle. And actually, we should consider all of them, but we took this one. And the reason why we have a match is because this chirality measures determines the scattering of the light. This and those, they may be a part of the structure, but they make much smaller impact on the scattering or absorption of the light. There are a number of applications of these chiral structures. Let me go and skip these pieces because I actually want to talk. I mean, I'm not sure how you're interested in catalysis, but this is something which can be applied quite interestingly and engineer the complex particles in this way. Understanding that a lot of effort in the center is on the connection between topology and properties of matter. I would like to give you some thoughts on how we have been working along the same direction, perhaps, on cartilage. So complexity is a good matrix, but it's a high-level descriptor. So it does not give you a very it doesn't give you a direct connection to, for instance, a stress transfer or charge transfer or heat transfer. It could say that complex structures are more useful, yes, and if you minimize the complexity, it will be of particularly easy to make. Yes, it can tell you that. But engineering of complex structures will require something more. And this is the direct connection between the properties and the structure at the granular level of the graph theory. And so cartilage, one of the examples that you saw before, is very good for this case. And it's a graph theoretical description based on the same ideas. So if there is a rod, doesn't matter if it's uniform or not uniform, it is a K2 structure. And when they come together, it will be a node, and we can easily describe this network of nanofibers as a graph. And in fact, it's not only applicable to the cartilage, but also to many, many other reticulated or percolated solids. And now, by using the software that we developed with Drew, we can actually extract that graph description straight from scanning electron microscopy images. So from that, we can analyze the graph theoretical descriptors that you see here. They are describing the connectivity between the different segments of the system. They describe the patterns in the system, and some of them are in short range. For instance, the parameter of graph density or degree. Others, like average nodal connectivity or clustering coefficient or closeness centrality, describe on progressively longer distance. So the clustering coefficient describes the triplets or the triangle, a little bit bigger. The closeness centrality is over the entire graph. Basically, a measure of short paths through the entire, through each node. This can be used to evaluate the transport or the different singularity points. And I would like to give you just a gist of that approach that we are developing now. For instance, we can make analogs of collagen or cartilage fibers from Kevlar, which are aramid nanofibers, which, by the way, are chiral, interestingly enough. We can also make some of the similar structures from gold wires. And by looking at this, and that, the same question arises: which of them are equally organized or equally complex as cartilage, for instance, this or that? We extract the graphs, we analyze them by using these topological parameters, and we can see now very clearly that gold nanowire networks, they're quite different from both aramid nanofiber networks and the cartilage. So they may look quite similar, but the graph theoretical parameters capture the difference, especially in the long-range organization of this network, which is due to the flexibility and arranging of the fibers. It has a direct representation in functions. And we compare, and if cartilage has the similar organization to aramid nanofibers, the latter should behave similarly as cartilage. And this is absolutely true. We, for instance, made the implantable devices, which are coated with aramid nanofibers, and indeed, cells recognize it immediately. They adhere to them very nicely and do not adhere to some other plastics. So, and after that, one can also develop it further, and I'll be happy to talk about it maybe in some other time. So these are awesome people who make my group. So they're hardworking, they're beautiful minds, they are exceptionally funny. They also have a lot of nice friends. You can see some of those. And my group is famous for its parties outside, non-alcoholic parties, and a large number of dogs that we have. Dogs are the way how we keep our sanity and continuing writing exciting papers. Thank you very much, and I will happy to answer any questions, and there are some other topics that we can talk more about.